All right, let's talk about the lime kiln. In any craft pulp mill, this thing is the absolute heart of the chemical recovery loop. And if it goes down, well, the entire plant is on the clock. This isn't just some textbook exercise. Understanding the chemistry happening inside this machine is what keeps the whole operation from grinding to a halt. So what you're looking at here, this massive rotating furnace, it has one and only one critical job. It takes the spent lime mud and cooks it, regenerating it back into active calcium oxide, what we call CaO. And that CaO, that's the chemical that drives the entire craft pulping process. If you don't have CaO, you're not making pulp. It is literally that simple. Okay, here's the plan. We'll start with the kiln's core job. Then we'll get into impurities, the real root cause of most problems. From there, we'll tackle the big one, ringing, which is a total kiln killer. We'll also touch on collateral damage like dust and brick wear, and then wrap up with a practical playbook for the operators. All right, first up, the kiln's critical job. We have to start with the calcination reaction because this is the fundamental chemistry that makes the entire recovery loop work. So it all begins back in the causticizer. That's where we make our cooking liquor. And in the process, we precipitate out calcium carbonate, CaCO3. That's our lime mud. We dewater it, then we feed it into the kiln. And inside, once it hits about 800 degrees Celsius, that's when the magic happens, calcination. The CaCO3 breaks down into the CaO we need, our good lime, and releases CO2. The entire reason this multi-million-dollar piece of equipment exists is to make this one reaction happen and close the chemical loop. Okay, section 2, impurities, the real root cause of failure. Now, that chemistry on paper looks pretty simple, right? But out in the plant, the process is never pure. All the headaches, the shutdowns, the lost production, almost all of it can be traced back to the small percentage of impurities that come in with the lime mud. So let's look at a typical composition. See that? 95% calcium carbonate, that's the good stuff. But it's this other 5% or so that we really need to pay attention to. And trust me, of all these impurities, the one that causes the most trouble, by a long shot, is sodium. You see it here listed as Na2O. And here's the thing. Not all sodium is created equal. You've got your water-soluble stuff from leftover liquor. That melts around 800 C and causes stickiness. Then there's the insoluble sodium, mostly locked up in silicates. It's relatively harmless. But the real villain here, the one that bites you in the field, is what's known as guarded sodium. These are sodium ions that literally get trapped inside the calcium carbonate crystal lattice itself. You can't wash it out, and it gets released at the worst possible time, right in the heart of the kiln where it can cause the most damage. This diagram here, this is really important. It shows how the sodium problem just compounds on itself. Down at the hot end by the burner, the sodium vaporizes. Then, that vapor travels with the hot gases toward the cooler feed end of the kiln. And what happens? It condenses back onto the fresh, incoming lime mud. So you get this internal enrichment cycle that concentrates the sodium right in the middle of the kiln. It's the absolute worst place for it to build up. Which brings us to section 3. All that concentrated sodium leads directly to the single most disruptive, costly, and honestly, the most infuriating problem you'll ever face in lime kiln operations: ringing. The kiln killer. And yeah, this is what it looks like. We're not talking about a small buildup here. This is a massive, concrete, hard obstruction that can literally choke the entire kiln. When a ring gets this bad, you're done. You have absolutely no choice but to shut down the whole operation for an expensive, miserable, time-consuming cleanout. That's lost production you are never, ever getting back. So how does this actually happen? It's a nasty little cycle. First, those sticky particles from the molten sodium start sticking to the refractory wall. Then, a soft layer of good lime, our CaO, builds up on that sticky base. Now, here's the kicker. Step 3. You get a drop in temperature, maybe the burner hiccups or the feed changes. That temperature drop is the trigger for step 4. That soft, fluffy layer hardens up through a chemical reaction. And then the whole cycle just repeats, over and over, building this ring layer by painful layer, getting harder each and every time. And that hardening reaction? It has a name: recarbonation. It's just the reverse of the main calcination reaction we want in the kiln. Our good lime, the CaO, reacts with CO2 from the flue gas and turns right back into calcium carbonate. But in this case, it's not lime mud anymore. It's basically cement. It's the binder, the glue that gives that ring its incredible concrete-like strength. And this chart, this shows you just how tough these things get. It's plotting compressive strength against temperature. And look at that spike. You hit peak strength. We're talking up to 60 megapascals. That's incredibly strong, right around 750 degrees Celsius. And wouldn't you know it, that's the perfect temperature for that recarbonation reaction to happen. It's just a perfect storm of chemistry and physics, and it's all working against you. Okay, moving on to section 4. So ringing is the big, obvious problem, but it's not the only consequence. The same root causes, that same tricky chemistry, also leads to other headaches, what I call collateral damage. Things like excessive dusting and just brutal wear on your refractory bricks. And this leads to a classic operator's dilemma. It's a real balancing act. See, high sodium makes everything sticky, and you get rings. So the obvious solution is to wash the mud better, get the sodium down. But if you go too low on the sodium, the lime particles don't clump together like they're supposed to. They don't nodulize. Instead, the whole kiln just fills with fine dust. So you're constantly walking this tightrope, trying to find that perfect sweet spot between ringing and dusting. Now, let's talk about the kiln lining itself. These refractory bricks, they are the only line of defense protecting that steel shell from insane temperatures and constant chemical attack from things like sodium. And if this lining fails, it's not a quick fix, not at all. We're talking a major, multi-week shutdown for a full rebrick. That's a huge capital expense and a massive, massive hit to your plant's availability. You know, when you're selecting refractory bricks, it's tempting to think, just get the highest alumina content, that must be better. But it's not that simple. Look at this data. For both 60 and 70% alumina bricks, the chemical damage actually gets worse as the corundum content goes up. The real key is the mineral structure. You want a brick with a higher molite content. That gives you much better resistance to the chemical attack from sodium. It's a perfect example of how deep material science has a direct impact on plant reliability. All right, final section. We've gone through the chemistry, we've seen the problems, so what do we do about it? Let's get practical. This is the operator's playbook for actually managing this machine day in and day out. Here's a simple on-the-floor troubleshooting guide. Think of it as symptom, likely cause, first check. So you see a ring forming mid-kiln. Your first thoughts should be high sodium or temperature fluctuations. So go check your mud washer efficiency and look at the burner stability trends. Lot of dust. That probably means your sodium is too low or your mud is too wet. Check your sodium levels and your mud solids percentage. High TRS emissions, that's total reduced sulfur. That's almost always unwashed white liquor getting into the kiln. Check your mud washing again and check the excess O2 at your burner. It's a very straightforward, practical way to diagnose problems. So when you boil it all down, real control comes from just a few key areas. First, on the input side, stabilize your mud solids and get your washing as good as it can possibly be to control that sodium. For the process itself, a stable burner is absolutely non-negotiable. You have to minimize those temperature swings. On the output, you got to monitor your residual CaCO3 to make sure you're not overburning the lime because that just eats your refractory for lunch. And finally, material selection. You have to have the right brick in the right zone. And this slide really puts it all together. This is where the theory hits the road. On the left, you've got a spec sheet for a refractory brick, all neat and tidy. And on the right, that's the hellish real-world environment it has to survive in. In that high-temp burning zone, you absolutely need a high alumina brick, something in the 60 to 70% range, with serious chemical resistance. You can see right on the table, a brick like one of these is designed for exactly that job. It has the strength, the resistance, and it's stable well over 1600 degrees C. So that brings us right back to the fundamental challenge, that operator's dilemma. We know for a fact that high sodium causes rings, but we also know that running with really low sodium can swamp you with dust. There is no single magic number that works for everyone. Every single kiln is different. It has its own feed chemistry, its own operational quirks. So the real question, the one that every single engineer has to answer for their own machine, is this: where is the optimal operating window for your kiln?